One way that we can analyze acid-base neutralization reactions is known as an acid-base titration. And it gives us a chance to sort of put together a few of the topics that we've talked about so far in this chapter, and that is the idea of molarity, the idea of solution stoichiometry, and the idea of acid-base neutralization. So let's see what's going on here. So most acid-base neutralization reactions that we've looked at follow a 1-to-1 neutralization, right? So we have 1 mole of hydrogen reacts with 1 mole of hydroxide to give you water, right? That's the neutralization part. So the idea is if we know the moles of, say, the acid, then we know the moles of base needed to react with it are going to be 1, right? We're going to be the same. So by using that stoichiometry of the balanced equation, the ratio, right, and understanding that idea, we know that when we do this kind of titration with most acids, the idea is that the moles of acid are going to equal the moles of base. Now, so what that allows me to do is to take a known concentration of either acid or base and add it to an unknown concentration of acid and base, and to calculate the one that's unknown, right? So it's a way to calculate an unknown acid or base concentration based on knowing the other one. So typically we have what's known in what's called a burette, right? So that's this thing here. And so in this example, it is our base. And we have some known volume of our acid solution, in this case, or known solution in the flask below. So we know the concentration in the burette. We know the volume below in the flask. And we're going to add what's in the burette. So in this case, we're going to add our base until we've added equal numbers of moles to the acid that we have. Now, how are we going to know when we do that? Well, we're going to use an indicator to note when we reach what's called the equivalence point. And the equivalence point is that point where the moles of acid equal the moles of base, right? That's the equivalence point. And the indicator will change colors at that equivalence point. So we're going to take this base that we know the concentration of, and we're going to add it, until the indicator tells me that at this point, moles of base added equal moles of acid that were in the flask, right? This is my equivalence point. Okay. So, let's say we have this problem. We have 23 milliliters of 0.15 molar KOH. It is added to 20 milliliters of HCl. Right? So we know the volume and the concentration of the base in our burette. So we know how much we had to add to get to this, to get to the equivalence point, and we know the volume of our, in this case, acid that was originally in our flask. Find the concentration of the acid. So this problem sort of looks similar to our solution stoichiometry problem that we had, right? Where we knew we had one reactant, and we wanted to figure out how much the volume of the other reactant we would need to react with it. Well, we can use a similar type of setup here. So we're going to start with what we know the most about, right, which is our base. So we have 23 milliliters. Now, we need this in liters. So let's remember that, I'll do it right here, that if I have sure, let's do it right here. If I have 23.3 milliliters, remember 1 milliliter is equivalent to 1 times 10 to the minus third liters. So my milliliters cancel out. And if I do my math, I'm going to get 0.02300 liters. So we're going to start with that number, 0.02300 liters KOH. Now remember, I need to figure out moles, right? So my pathway here, if I want to diagram a pathway, right, it's going to be volume of KOH to moles of KOH to moles of HCl, right? And this is ultimately what I need to find through my stoichiometry. So to go from volume to moles, right, what do we use? Molarity. Right? So what's the molarity of my KOH? Right? It is 0.15 moles KOH per 1 liter of solution. So my liters of KOH cancel, liters of KOH solution cancel. Now I need to go from moles of KOH to moles of HCl. Well, this is where my equation, so we understand that moles of acid equal to moles of base. So I have 1 mole of HCl for every 1 mole KOH. This serves to change my units. And so if I do that math, I end up with 0.0035 moles of HCl, right? 2 significant figures because I'm limited by the molarity of the KOH was only 2 significant figures. Now, I have my moles of HCl. Now, what I was asked to find was the molarity, or the concentration, of the HCl. So, what is molarity? Remember, molarity of HCl is going to equal moles of HCl divided by liters of HCl solution. So I know my moles of HCl, 0.0035 mole. what was the volume of HCl in my flask? Well, I had 20 milliliters. So this is going to be 0.020 liters. Right? So we do our milliliters to liters conversion. So we do moles divided by liters. And this gets me to 0.175 molar HCl. Okay. So the acid-base titration is just a tool that we can use to analyze acid-base reactions, where we take advantage of the idea that 1 mole of base will neutralize 1 mole of acids, and so it gives us a tool to find out, to calculate the concentrations of some unknown acid or base solution if we neutralize it with an acid or base solution that we know the concentration of. Okay. So acid-base titration. Now I want to talk about a final type of aqueous reaction that also, again, follows the double displacement pattern that we've been talking about. And that is a gas evolution reaction. And not unlike the precipitate reactions that we saw later, these are reactions where we have reaction of an aqueous solution of an ionic material with, in this case, an acid to produce a gas along with other products. So let's look at some of these. So again, this is going to be the reaction between an aqueous ionic compound plus an acid is the reaction that we're looking for. Now, these reactions fall into sort of 2 basic types. So if we look at the table here, we have these bottom 3 here, which go through what we might term an intermediate. And in these reactions, we form an intermediate product before the ultimate gas reaction is formed. So if I look at the reaction in the picture here, we see the reaction between sodium bicarbonate and hydrochloric acid ultimately forms our gas, which is carbon dioxide here, along with water, right, and an ionic material. But if we look a little deeper, before we get to the formation of the water and the carbon dioxide, if we look at the double displacement, what we see is the initial formation of the intermediate they were talking about. So if we look at this, if we take the sodium HCO3 plus HCl, the initial double displacement, right, would combine the sodium with the chlorine, of course, and the H plus with the bicarbonate ion. And so you get H2CO3 plus NaCl. And this is the intermediate that we spoke about, and it's this carbonic acid here, right? This is carbonic acid. That ultimately breaks down to give you water plus carbon dioxide. So these bottom three types are different versions of this type of gas evolution reaction, where if we follow the pattern, we have some sort of aqueous ionic material, either a carbonate or a bicarbonate, or a sulfite or a bisulfite. Right, so these are types of polyatomic ions, right, that we should be familiar with. And upon reaction, they form these types of intermediates, which ultimately break down to a corresponding gas, either CO2 or SO2 plus water. You also have one that involves ammonia, right? Ammonium, right? So remember, ammonium is another polyatomic ion, and so when you get ammonium compounds, right? This ionic compound with the ammonium ion reacting in this case not with acid but with a base, you get the initial formation of this ammonium hydroxide is what the double displacement would tell you, but that ammonium hydroxide breaks down to ammonia gas and water. Now, the other kind of gas formation reaction, there's one type, and this is a direct formation. And this occurs when we react a sulfide, like K2S, like potassium sulfide, with an acid, and we get direct formation of dihydrogen sulfide, right, or hydrogen sulfide gas, H2S, again, along with an aqueous ionic compound. So we can get direct formation of H2S gas, or we can get formation of we can get direct formation of CO2, SO2, or ammonia via some intermediate process. Okay, let's look at this one example here. And again, let's do our double displacement. We have HCl plus calcium, and there's a typo on the slide. This should be calcium sulfite, SO3. And so if we think about the ions present, right, the acid will have H plus and Cl minus. You'll have Ca2 plus and SO3 2 minus. The ions exchange, the hydrogen goes with the SO3 2 minus, the chlorine goes with the calcium to get H2SO3, and the calcium combines with two chlorines, we get calcium chloride. Now, if we look at our solubility rules, we would see that that's going to be aqueous. And here, and this is what part we really do have to kind of sometimes memorize these intermediates. When we spot this H2SO3, this sulfurous acid, right? So this is sulfite, so the acid is going to be the us acid. So we see sulfurous acid here. we recognize that this breaks down to water plus SO2 gas. And so my overall reaction, of course, is going to be HCl plus CaCO3, and we added it in a solid form as opposed to an aqueous form. It's going to break down to give you water, SO2, plus the calcium chloride aqueous. And so gas evolutions. So a third sort of classification of these aqueous reactions that we've been looking at. And so as a little review here, we talked about precipitation reactions, right? These are reactions that form a solid when combining two aqueous ionic compounds using solubility rules to determine that. We had acid-base neutralization reactions, where we have an acid plus a base gives you ultimately water plus typically an aqueous ionic compound. And we have gas evolution reactions, which involve typically the reaction of some ionic compound with usually an acid or a base in the case of ammonium, and they lead to the production of a gas along with water and some aqueous ionic compound. Now, I will have also posted other types of videos or other videos that will go over some of these ideas and expand upon some of them. So, for example, I will probably have an acid-base video posted that goes beyond, a little bit beyond what we're going to cover, to sort of add some depth, but ultimately be responsible for the material that's covered in the book or in the slides. In our next section, we will look at our last sort of sample type reaction that we're going to overview, and these are what are known as redox reactions.